x of t is a real with autocorrelation. It's a wide sense stationary process, and with autocorrelation Rx of tau, and PSD is Sx of omega. So we have to prove that the autocorrelation is real and even, and the power spectral density is even and positive. Okay, now we know that our autocorrelation depends on only the time difference t1 and t2. So if xt1 is complex, then xt2 will be the complex conjugate of that, and only that, thus we can get the autocorrelation is a function of the time difference. So multiplying a complex with its conjugate always gives us a real number, so we can say the autocorrelation is real valued. For the autocorrelation to be even, we have to find out Rx of tau is equal to Rx of minus tau. So if we can write Rx of tau as expectation of xt into x of t plus tau, since the time difference between those two is now tau, okay, then Rx of minus tau would be expectation of xt into x t minus tau. Okay, now since it's a wide sense stationary process, we can add tau amount of time to both of the signals and still get the same statistical properties. So adding tau in the second equation, we can find that it now becomes expectation of x of t plus tau into x of t, so which is now first equation. So the rxx of tau is now rxx of minus tau, so we can say that the autocorrelation is an even function. This is the equation for the power spectral density, and expected power at 0 is equal to the second moment of expectation. So we can say that the second moment is a positive value, so the integral will have a positive value in the end. Okay, and we can also say that the energy of a signal is always positive, since energy is a positive quantity. For the signal to be even, the same formula we apply here, the PSD of minus omega. Now we just change the value of tau from positive to negative, and we find that since r of minus tau is equal to r of tau, we proved that already, and the sign of the integral now changes to minus, and but the range is now from positive infinity to negative infinity. So if we switch that again, then it becomes the old equation of sxx of plus omega. So just like this equation, so we can say that sxx of omega is an even function. For number 3, xt is a wide sense stationary process, output is yt, and the impulse response is ht, and we need to find out if yt is wide sense stationarity or not. So for wide sense stationary, we can find out that the expectation would be a constant value, and the autocorrelation is only dependent on the time difference, that's tau. Now using the formula of convolution, we can find the expectation and the mean of yt, that eta y of t is equal to eta x of t convolution ht, and since eta h is a constant, so we can put that out of the equation. Yeah, now let's find out ryy of t1 t to the autocorrelation of y for y. Okay, so it's the expectation of x t1 into yt2. Now using, now we're breaking yt2 into the convolution integral, and then using some algebra we can find out that it now becomes the autocorrelation for x t1 t2 convolution ht2. Sorry, this was the rxy. I need to correct that. And for the next step, ryy of t1 t2 would be just the expectation of yt1 yt2, and again using the convolution integral we can find out in the end that it's nothing but the autocorrelation of x t1 t2 with convoluting it with ht2 and then ht1. Now since xt is wide sense stationary, so the autocorrelation depends on time difference tau only, so we can rewrite the equation like this. So now it's t1 minus t2 plus alpha h alpha d alpha, the integration, and since t1 minus t2 or t2 minus t1 both of them are tau, and let us change the value of alpha to minus u, So we can get d alpha is equal to minus du. Then using the algebra inside the integral, we can find out that in terms of tau, we are writing the equation, the autocorrelation of xy t1t2 would be rxx tau convolution h of minus tau. Now let us replace this inside the autocorrelation of y t1 t2, and then using that we can, in terms of tau, we are getting the output as rxx tau convolution h of minus tau convolution h of tau. So this is a function of tau only. So since this is a function of tau only, and previously we found out that the expectation doesn't depend on, it's a constant, so we can say that yt is also White's stationary process.